Ever pondered about how much you truly know about electricity? This invisible force is a fundamental part of our daily life, powering everything from the humble light bulb to the complex computer systems that keep our world running. Yet, for something so integral, many of us know surprisingly little about how it works. And that's a shame, because understanding electricity can unlock a world of practical applications. Whether you're an aspiring inventor, a DIY enthusiast, or just someone who wants to understand how the world works, a basic knowledge of electricity is a powerful tool. So let's embark on this electrifying journey together, because understanding electricity starts with grasping the concept of electric charge. So, what is electric charge? Well, in the simplest terms, it's a fundamental property of matter. There are two types of electric charges that exist, positive and negative. They're like the north and south poles of a magnet. Just as opposite poles attract, positive and negative charges pull towards each other, while like charges repel. This interaction between charged particles forms the very foundation of electricity. It's a bit like a dance, with particles constantly pushing and pulling, creating the energy that powers our world. So the next time you switch on a light or charge your phone, remember it's all down to these tiny charged particles doing their intricate dance. And the role of atoms in this process is simply fascinating. Ever wondered how tiny atoms contribute to electricity? Let's dissect an atom to understand better. An atom, the smallest particle of an element, consists of a nucleus surrounded by a cloud of electrons. These electrons, with their negative charge, are free to move, and it's their movement that creates electricity. Now let's think about different materials. Some, like copper or gold, are conductors, allowing electrons to move freely and electricity to flow. Others, like rubber or glass, are insulators, hindering electron movement and resisting electricity. Then there are semiconductors, the Goldilocks of materials, that can both conduct and insulate under different conditions. This interplay of atomic structure and material properties sets the stage for electrical conductivity. The flow of these electrons is governed by three key concepts: voltage, current, and resistance. Imagine trying to understand the flow of electricity without understanding these three concepts. At the heart of electricity, we have voltage, current, and resistance. These three concepts are like inseparable companions, always working in tandem to make the magic of electricity happen. Let's start with voltage. Think of it as the force that pushes electric charge around a circuit. It's the energy per unit charge, like a team captain encouraging its members to keep going. Next, we have current, the flow of the electric charge. Picture it as a river where the water represents the electric charge, and the speed at which the water flows is the current. Lastly, we encounter resistance. As the name suggests, it's about how much a material opposes the flow of electricity. Imagine it as rocks in our river slowing down the water's flow. The bigger the rocks, the greater the resistance, and the slower the current. These concepts are interrelated. Voltage drives the current and resistance slows it down. It's a delicate balance that keeps electricity flowing in a controlled manner. So, you see, understanding voltage, current, and resistance is like unlocking the secret code to electricity. These concepts are encapsulated in a powerful law known as Ohm's law. What if there was a simple equation to understand the relationship between voltage, current, and resistance? This brings us to Ohm's law, a fundamental principle in the world of electronics. The law, named after the German physicist Georg Simon Ohm, states that the voltage across a conductor is directly proportional to the current flowing through it. Simply put, V equals Y times R. Let's think of a practical example. If you have a toaster plugged into your kitchen outlet, the voltage is like the pressure from the outlet pushing the current or flow of electricity through the resistance, which is the toaster's heating element. This law helps us to understand the behavior of electric circuits. It's a cornerstone of electronics, and it's as simple as V equals I times R. Did you know electrical devices can be connected in more than one way? Indeed, there are two main types of electric circuits, series and parallel. In a series circuit, devices are daisy-chained one after the other like a line of dominoes. The current has one path to follow, and if one device fails, the whole circuit goes dark. On the other hand, in a parallel circuit, devices are connected side by side like lanes on a highway. Each device has its own path to the power source. So if one fails, the others keep on shining. This is how most of our household circuits are set up. The way we use these circuits directly affects power consumption. So, understanding them is key to using electricity efficiently and safely. Fascinating, isn't it? Power consumption is a hot topic these days. So what is electric power? Simply put, electric power is the rate at which electrical energy is transferred by an electric circuit. It's like how fast water is flowing through a pipe. The unit of electric power is the watt, named after James Watt, the 18th century developer of the steam engine. When we talk about power consumption, we're referring to how much electric power is used over a period of time. This is measured in watt-hours. For example, a 100-watt light bulb running for 1 hour consumes 100 watt-hours of energy. So, when we think about reducing energy usage, it's not just about how many devices we have plugged in, but also how much power each device consumes and how long it's used for. It's important to note that not all electrical currents are the same. Have you ever pondered the difference between alternating current and direct current? Let's dive into it. In the world of electricity, there are two primary types of current: alternating current, or AC, and direct current, or DC. AC is the type of electricity that powers our homes and offices. It's called alternating because the flow of electricity changes direction periodically. On the other hand, DC, or direct current, flows in only one direction. This is the type of current you'd find in a battery-operated device, like a flashlight or a mobile phone. The main difference between the two lies in the direction of flow. AC's changing direction makes it easier and more efficient to transmit over long distances, which is why it's used for power grids. DC, with its unidirectional flow, is more stable and efficient for low-distance devices, hence its use in batteries. Regardless of the type of current, safety is paramount when dealing with electricity. How often do we consider safety when using electrical devices? It's a question worth pondering, isn't it? The importance of electrical safety cannot be overstressed. The invisible force of electricity, while being indispensable in our daily lives, can also be a silent hazard if not handled with respect and caution. Firstly, always switch off and unplug electrical devices when they are not in use or during maintenance. It's as simple as that, yet it's a practice often overlooked. Secondly, never overload sockets. It's tempting to plug in one too many gadgets, but remember, overloading can lead to overheating, and in the worst-case scenario, a fire. Thirdly, keep electrical devices away from water. Water is a potent conductor of electricity and can lead to accidental shocks. Lastly, always call a professional when dealing with complex electrical issues. A bit of DIY is good, but not when it comes to electricity. While safety is crucial, it's also exciting to look ahead at what's coming. Oh, curious about the future of electricity? Well, let's take a sneak peek. As we strive for a sustainable future, the field of electricity is not left behind. The world is witnessing a surge in research and development of emerging technologies, all aiming to revolutionize how we generate, distribute, and use electricity. Take, for instance, the innovative concept of smart grids. These are designed to enhance the reliability and efficiency of our power systems, incorporating renewable sources like wind and solar energy. Then there's the exciting realm of energy storage, with advancements in battery technologies playing a pivotal role. And let's not forget about electric vehicles, a rapidly growing sector that's reshaping our transportation systems and energy consumption patterns. From smart homes to wireless power transfer, the future of electricity holds a promise of a more connected, efficient and sustainable world. As we look to the future, let's not forget the fundamental concepts we've explored today. So, how much more do you know about electricity now? We've journeyed through the world of electricity, from delving into the basics of electric charge and the role of atoms, to understanding the relationship between voltage, current and resistance. We've simplified Ohm's law and differentiated between series and parallel circuits. We've also explored the concept of electric power and energy, and the differences between alternating and direct current. We've touched upon the importance of electrical safety and looked forward to future trends and innovations in the field of electricity. It's clear that the world of electricity is vast and ever-evolving, with new technologies and sustainable energy sources on the horizon. Let's continue to appreciate the marvels of electricity, not just as a convenience, but as a fundamental aspect of our lives. Encourage your curiosity and continue to explore this fascinating field. Remember, electricity is not just a convenience, it's a marvel of nature that powers our world.